Now let's say that instead I took a particle here and I was taking a particle here. So instead of doing that, let's say what happens between these two particles. You see that this particle at x1 is at its maximum, this particle at x2 is at its minima. Now what is this distance? This distance, as you can see, is lambda by 2. Okay. Now to reach to this position, how much addition in phase should I do? You know that y is equal to y1 sine of at x1 the angle was alpha. Now you see that this displacement in y direction is just the negative of this displacement. So if I write this as y1, y2 is minus y1, or I can write y2 as minus a1 sine of alpha. Now I can write this also as a1 sine of alpha plus pi. So you can very well see that moving ahead a distance of lambda by 2 is equivalent to adding a phase of pi. Now from here, let's say I take a point here. These 2 points are in phase because you see that at any time t, this and this displacement are same. So this distance is lambda. So these two are in phase, these two are out of phase, because when this is maximum, this is minimum, this is minimum, this is maximum. So I can also write that these and these are out of phase because these two are in phase, these two are out of phase. So these two are out of phase. So I can write this as a1 sine of pi plus, again a distance of lambda units, means adding 2 pi. So I can write that lambda by 2 was equal to addition of pi. Lambda by 2 plus lambda was equivalent to adding of pi plus 2 pi. You know that lambda by 2 plus k pi is equivalent to adding a distance of pi plus 2k pi, because k lambda here, k lambda is equivalent to 2k pi. So I can write that if I take lambda common, here I get 2k plus 1 pi. So you see that for any position x, if I take points at a distance of lambda k plus half units away, then I get points like this, which are completely out of phase with these points. When I say completely out of phase, what I mean is when this particle at x1 is at its maximum, this is at its minimum. When this is at its minimum here, this is at its maximum here. When this is 0, this is also 0. So basically what is happening is, it's some sort of, you can say that the displacement at x2 y2 is equal to minus of y1. So this is when we call that the displacements are out of phase, or the particles at 2 points are out of phase. Now let's say that I have a point x here. Now let's say that there are 2 points s1, s2. A wave is coming from s1. So since a wave is coming from here, when the wave reaches here, let's say that because of this s1, there's a displacement in y direction, because wave is basically a disturbance. So when the disturbance reaches here, there's a displacement in y direction. Now what happens when a wave from s2 also strikes this? What happens? This wave interferes with the displacement produced by this wave, and this phenomena is known as interference, because this wave at s2 is interfering with the wave of s1. Now s2 interferes with s1. So what happens? S2 interferes with the displacement produced by S1. So finally what happens? The final displacement is the resultant of the displacement produced by S2 and S1. See, S1 tries to produce a displacement, S2 also tries to produce a displacement, and the final displacement is the resultant of the vector sum of the displacements produced by both the waves. Now how do I find that? I find that using the superposition principle. So what I do, I find out what is the displacement produced by S1, and then I find out what is the displacement produced by S2, and then I add them vectorially. So if the displacement produced by S1 is, let's say, 5 centimeter, and the displacement produced by S2 is, let's say, minus 2.5 centimeter, the final displacement here will be 2.5 centimeter in this direction. Similarly, if the displacement produced by S1 is 5, S2 is also plus 5, both the displacements get added up, and we have a displacement, net displacement in this direction, known as 10 centimeter. Okay, now let's say that this distance is x1 and this distance is x2. So what is the equation of the wave reaching here due to S1? I can write this as, let's say, a1 sine 2 pi by t minus 2 pi by lambda x1 plus some phi 1. The equation of the wave coming from S2 will be a2 sine 2 pi by t minus 2 pi by lambda x2 plus phi 2. Now, if I say that these two waves arrive in phase at this point, that means what? When I say that these two waves arrive at this point in phase, that means what? This angle, let's say alpha 1, this angle, let's say alpha 2, are always same. Is it? Is it alpha 2 is always equal to alpha 1? When I say that the two waves always arrive at this point in phase? No. See, as I told you that if I have a wave, if this was the point x1, then particles or at a distance of k lambda were in phase. So, which in terms of phase, I told you that if at x1 phase was alpha 1, then at phases of alpha 1 plus 2k pi, the distance is x2, x3, x4, whatever points we get at phases of alpha 1 plus 2k pi, all the particles are in phase, as I told you. So when I had a wave like this was in phase with this was in phase with this had a phase of alpha, this had a phase of alpha plus 2 pi, this had a phase of alpha plus 4 pi. Similarly, all the points which had a phase of alpha plus 2k pi were in phase with this point. So when I say that these two points are in phase, these two waves are in phase here, that means what? If this is alpha 2, this alpha 1 has to be some value like alpha 2 plus 2k pi. Because as I told that for any point x1, displacements at phases of alpha plus 2k pi were in phase. So similarly, if these two waves are in phase here, if this has a phase of alpha 2, this has to have a phase of alpha 2 plus 2k pi.